and welcome to this tutorial. In this tutorial, we'll solve a simply supported beam with a point load at an angle and a UDL, a uniformly distributed load. If you at this point are feeling quite confident with reactions and free body diagrams, feel free to skip ahead straight to the part where we start cutting and analysing the beam. Let's get to it. Okay, let's quickly start off by finding the reactions. As I mentioned, if you're feeling quite confident that you know how to find the reactions, feel free to skip ahead. Before I find the reactions, what I'm going to do is I'm going to take this force of 18 and I am going to divide it into its components. So I've got this force here of 18, it's at a 60-degree angle, so I know that it's comprised of two forces, this force here going in the negative x and this force here going in the negative y. Since this force is 18 kilonewtons at an angle of 60, this here is going to be 18 sine 60, which works out as 15.58. And this here is going to be 18 cos 60, which works out as 9 kilonewtons. I also know that I've got a pin support, so I can replace that with two forces, AY and AX. And at D, I have a roller support, which I will replace with one force, DY. I'm also going to, for my free body diagram, replace that 18 kilonewtons with the two components, just to make it easier for me to figure out where there's axial load and where there's shear load. So let's quickly do that as well. So just get rid of this, and I'm going to add in here this force going down of 15.58 and this force here of 9. And now we're ready to find the reactions. So starting off with the sum of forces in the x direction, with this being my positive x, I've got AX minus 9 equals 0, so AX works out as 9 kilonewtons. Next thing I'm going to do is the sum of moments around A, with this being my positive direction. So starting from left to right, I've got this 15.58 giving me a negative moment, so 15.58, and times 2 meters till A. 9, you can see, passes through A, so it doesn't contribute to a moment. So just remember, if you have a force in the x direction, it needs a distance in y to contribute a moment. There's no distance in y here. The next thing we have is the UDL. So first thing, the equivalent force. So that is going to be the shape. So 6 times 4 in this case. So just a reminder, this is the area of the rectangle, and that is the force. And the distance is going to be from the centroid of that rectangle, so times half of 4, so 4 over 2, plus the rest of the distance that I need in order to get to point A. So plus 2, so plus 4 here. And then I've got dy, which gives me a positive moment, so plus dy, and the distance is the whole distance, so in this case 8 meters equals 0. And that gives me 8 dy equals 175.16, and if I divide everything by 8, I get that dy equals 21.9 kilonewtons. And the last thing that I'm going to do is the sum of forces in the y direction, with this being my positive direction. And in this case, I've got AY plus dy minus 15.58 and minus the force given by the UDL, which, as we said, is 6 times 4. And just a reminder here, that is the area, which equals the force. And all of that sums up to 0. So AY is going to be 39.58 minus dy, which we already calculated as 21.9 17.9, and that equals 17.68 kilonewtons. And now that I have the reactions, I can create my free body diagram by replacing these unknowns with the actual values. So let's just do that. AY is 17.68, AX is 9, and dy is 21.9. And now that we've calculated our reactions and created our free body diagram, we are ready to discover the internal forces in the beam. So let's figure out where we need to cut the beam and calculate the internal forces. Okay, so if I look at the beam first to discover where we're going to cut, I can see that between A and B, I start off with my reaction forces, so I'll probably want to know what they contribute to the internal forces. B gives me an extra load, so definitely want to know what's happening here. And I'll also want to know what happens between C and D when I have my UDL. So 3 cuts. Okay, starting off with the cut A to B. Let's draw out our part of the beam. Here we've got this force of 17.68. We've got this reaction force of 9. We don't have anything else between A and B. X1 is going to start from here, and X1 is going to be between 0 and 2 when I'm going to start my next cut, when I have this new force that comes. And I've now exposed these internal forces, so let's draw them all out. NX1, SX1, and MX1. Let's start off by doing the sum of forces in x equals 0. That'll help me find the internal axial load. So in this case, I've got nx1 in the positive direction plus 9 equals 0, and that gives me nx1 equals minus 9 kilonewton, meaning that the axial force here is in compression. Moving on to the sum of forces in the y direction equals 0, with this being my positive direction, I've got minus sx1 and then plus 17.68 equals 0. So sx1 equals 17.68 kilonewtons. And we can see here that that is just a constant throughout this cut. And the last thing is the sum of moments at the cut equals 0. So I've got my positive internal moment, mx1, and minus 17.68 times x1 equals 0. And so therefore mx1 equals 17.68 x1. And that is my equation for moment. Now for the moment, I'd like to look at a few interesting points. So I'll start off what happens when x1 equals 0 and what happens when x1 equals 2. So the two boundaries of this equation. So I can see that when x1 equals 0, I get 0, and when x1 equals 2, I get 35.36 kilonewton meters. And that gives me 2 points that I can put on my graph. Now before we move on to the second cut, let's just put in a place here for everything. So I'm going to draw my axial load here, my shear force will go here, and my bending moment will go here. And I can start off by drawing some of these things. So I can see here that my axial force from A to B is negative 9, and that's a constant. My shear force is also a constant, and it is 17.68. So let's draw that on as well. So just a straight line here, and 17.68. And my bending moment started at 0 and made its way to 35.36. Now I assumed here that this moment was positive in this direction, like that, meaning that it's pulling and creating tension on the bottom, pushing and creating compression on the top, and therefore I know that I need to draw on the tension side, which is at the bottom, and I can see that I will just have here 35.36, and I know that this is linear between them because it's just a function of x, so it's going to be a straight line in between those two. My second cut is going to be from B to C, and once again I'm just going to draw out the beam. So here I've got, in terms of the distance, I'm going to have already passed my 2 meters, and x2 is going to start from here. So in this case, I've got two reaction forces, the 17.68 and the 9. I've then got these two forces from that concentrated load that was at an angle, 15.58 and 9, and I've also got these exposed internal forces, so N x2, S x2, and the bending moment M x2. So just like before, we're going to go through all the equations of equilibrium, sum of forces in x, sum of forces in y, and sum of moments around the cut, and find out what those internal forces are. Starting off with sum of forces in x equals 0, with this being my positive direction. So I've got N x2 plus 9 from that reaction force, and then minus 9 from that concentrated load equals 0. So N x2 is going to be 0 throughout this cut. Moving on to the sum of forces in y equals 0, I've got minus S x2 plus the reaction force of 17.68 minus 15.58, and that's it in terms of the y direction, so that equals 0. And S x2 works out as 2.1 kilonewtons, and this is also constant throughout the cut. And then the last thing that we need to do is the sum of moments around the cut, with this being my positive direction. So here I've got this internal moment, and then starting from left to right, I've got negative 17.68 times 2 plus x2, that's my distance, and then I'm going to have a positive 15.58 times x2. And if I just isolate mx2 and add the two components that contribute to x2, I'll find that I get 35.36 plus 2.1 x2. So that's my equation for moment. And just like always, I'm going to figure out what are some important points that I want to find my moment. So what happens when x2 equals 0? And what happens when x2 equals 2? So those two extremes of this cut. At 0, I get 35.36 kilonewton meters, and that is really good because that is where I ended on the previous cut, and so this gives me a good indication that I'm right here. There would only be a jump in moment if there were a concentrated moment at that point, and there isn't. If I substitute 2, I find out that I get to 39.56 kilonewton meters, and those are my 2 points. So now we can put everything on the graph. Starting off with my axial force, I can see that I go from minus 9 to 0 for the whole of this cut. In terms of the shear force, I jump from 17.68 to 2.1, so we go down here to something quite small, that's 2.1 there. And in terms of my moment, I go from this 35.36 to a slightly higher, let's say just something like here, 39.56. And this is linear, so it's just going to be a straight line there. And now I'm ready for my third and final cut. This is going to be between C and D. And if I draw out my beam, I've gone through 2 meters here, another 2 meters, and x3 is going to start from here, and that x3 is going to be between 0 and 4 meters. So in that case, I've got my two reaction forces here, 17.68 and 9. I've got the two components from my load, which were 9 and 15.58. And I've also got this UDL starting up. Additionally, I've got all my internal forces exposed, so N x3, S x3, and the bending moment M x3. And that's it. We need to once again go through all the equations of equilibrium and find those internal forces. So starting with the sum of forces in the x direction, I've got N x3 plus 9 minus 9. Nothing else has been added in the axial direction. So once again, I've got N x3 equals 0. Moving on to the sum of forces in y, I've got minus S x3 plus 17.68 minus 15.58, and now I also have this bit of the UDL. So the force is going to be the area under the UDL, and in this case it's negative, right, because it's going down the way. So 6 is going to be the height of that rectangle, and x3 is going to be the width of that rectangle, whatever that might be, between 0 and 4. And that equals 0. So if I write that out, I find out that S x3 equals 2.1 minus 6 x3. In terms of points of interest, let's see what happens when x3 equals 0 and what happens when x3 equals 4. The two boundary conditions of this cut. So when x3 equals 0, I can see immediately that I get 2.1 kilonewtons, and that makes sense because there hasn't been a big jump, right? A UDL has just started, so there's no jump in the shear forces. So I'm starting really where I was before, 2.1. That's good. Let's give that a little tick. When I reach x equals 4, I find that I'm at minus 21.9 kilonewtons. Now this means that I've gone from plus to minus. I have passed through 0. I know that when the shear equals 0, I'm at my max or minimum moment. So I want to find out where is the shear 0, because that will give me min max moment. So let's take our equation and equate it to 0. So x s3 equals 2.1 minus 6 x3. When that equals 0, I can see that 2.1 equals 6 x3, and x3 works out as 0.35 meters. So let's just put the two things that we found before we proceed to the moment. So in terms of the axial force, we just found that that's a continuation of 0. In terms of the shear force, we discovered that we go from 2.1, which is this place here, and we go to minus 21.9, so something like that. This is minus, and this is 21.9. And I know that this distance here, between here and when I get to 0, is 0.35 meters. And I'm just going to drag this down here, because that'll be where I get my min or max moment. Okay, so let's move on to finding that moment. That's the last piece of this puzzle. So sum of moments at the cut equals 0. Let's see what we've got. We've first got this x3, the exposed internal moment. Then we've got minus 17.68, and this time the distance is 2 plus 2 plus x3, so 4 plus x3. We've also got the concentrated load of 15.58, which creates a positive moment of 2 plus x3. And finally, we have our UDL, and that creates a positive moment of 6x3. That is the area, right? So that gives me the force, okay, the area, which is the force. And then the distance for that is going to be x3 divided by 2, right? So it's always going to be this from the center of that rectangle until the cut, and that equals 0. I can isolate the moment and write this out as minus 3x3 squared. So I can see this is parabolic, plus 2.1 x3 plus 39.56. Let's look at some critical points here. What happens when x3 equals 0? What happens when x3 equals 4? So the two boundaries of this cut. And what happens at that point that we've just found when x3 equals 0.35, because I know that's going to be the max or minimum moment. So when x3 equals 0, I can see from this equation that the first two terms are 0, and I end up with 39.56 kilonewton meters. And that is great because that matches where I'm at. When x3 equals 4, I can calculate that. And if I do, I find out that that is 0, which is also a really good sign because I am expecting to be at 0 moment at the end of the simply supported beam. And the last point I wanted to check was the min-max. And if I substitute 0.35 into my equation, I find out that the moment is 39.72 kilonewton meters. So not massively higher, but that is the max. So let's draw this on. So I've got slightly higher here, and I go to 0, but this is parabolic, so it'll be like that. So that is a parabola, and up until here, these two were linear. And that's it, we found all the internal forces. Let's just have a quick look at our graphs and recap some of the important things. So what can we see here? We can see here that we've got an axial force between the reaction force and that concentrated load of -9, which means that this area here is in compression, and then after that there's no axial force. I can see here in the shear force that when there is a jump, either in the reaction and here, where there's this load, that jump is 15.58. Each jump that we have is at the value of that point load that's been added. And I can see here in the moment, the highest value of moment is when the shear crosses 0, and that is here. That was 39.72. When I have a UDL, I have a parabolic line, and when I have just point loads, I've got linear lines, okay? And these linear lines, they change the slope when I add a new force. So for example, here, where new force has been added, you can see that the slope changes. And here, where the UDL starts, obviously it's moving from a linear line to a parabolic line. In this tutorial, we saw the internal axial, shear and bending moment of a simply supported beam with a point load at an angle and a UDL. Join me next time for more interesting beams. Bye for now.